File Systems by Aakriti Tayal, Anchita Goel, and Sonia Dalal. File systems in Linux are known by ext, which is extended file systems. We have different versions of it, ext2, 3 and 4. The only difference between ext2 and 3 is that 3 has journaling. ext4 is a much improved version as it has more maximum individual file size as well as overall system file. ext2 is usually preferred on flash drives, USB drivers, as it doesn't need to do the overhead of journaling. It requires FSCK to recover data after unplanned reboot. Like I said, ext3 is exactly same as ext2 except for journaling. So what exactly is journaling? Journaling file systems avoid file system corruption by maintaining a journal. The journal is a special file that logs the changes destined for the file system in a circular buffer. At periodic intervals, the journal is committed to the file system. If a crash occurs, the journal can be used as a checkpoint to recover unsaved information and avoid corrupting of the file system metadata. Updating file systems to reflect changes to files and directories usually requires many separate write operations. This makes it possible for an interruption like a power failure or system crash between writes to leave data structures in an invalid intermediate state. For example, deleting a file on a Unix file system involves two steps: removing its directory entry, then marking space for the file and its inode as free in the free space mapping. Now we have a small video to show you to explain the concept of journaling in an easy manner. So today we're going to learn a little bit about journaling file systems. So journaling file system basically captures all your metadata, which is the date, time, and the action that is to be performed. In this case, which is pull out 3 chairs. Then our next entry, which again includes the date, time, and action, which is put in 2 chairs. Then our third entry, which is put back 1 chair. But suddenly the power goes off, but have no fear, when journaling file system is here, it basically reads the last entry and checks if the action has been performed or not. In this case it hasn't, so it does so. And ta-da! There are 3 types of journaling available in ext3 file system: journal, ordered, and write back. In journal, metadata and content are saved in the journal. In ordered, only metadata is saved in the journal, and the metadata are journaled only after writing the content to disk. This is default. Write back, only metadata is saved in the journal. Metadata might be journaled either before or after the content is written to the disk. ext4 is a much better version as several new features have been introduced in it: multi-block allocation, delayed allocation, journal checksum, fast FSCK. These new features have improved the performance and the reliability of the file system when compared to ext3. Now we have there are a couple of methods to identify your file systems, which we'll be showing you in just a moment.
HFS Plus file system. HFS Plus is a file system developed by Apple to replace their HFS hierarchical file system as the primary file system used in Macintosh computers or other systems running on Mac OS. It is also one of the formats used by the iPods. Now we will look at the features of HFS Plus. The maximum file size supported is 8 exabytes. Maximum number of files is 2 raised to the power 32 minus 1. Maximum file name length is 255 characters. Continuing with the features, HFS supports access control list based file security. It is a journaled file system. HFS plus volumes are divided into sectors, which are then grouped together into allocation blocks, which can contain one or more sectors. HFS Plus uses a full 32-bit allocation mapping table rather than HFS's 16-bit. In the figure, on the right-hand side, we have HFS Plus allocation blocks, and on the left side, we have HFS allocation blocks. The comparison shows that we have large number of HFS Plus allocation blocks, making it more significant. HFS Plus supports hard links to directories. Now we will look into the broad structure of HFS Plus. The bulk of an HFS Plus volume consists of 7 types of information or areas. Starting with the first one, volume header, which stores a wide variety of data about the volume itself. Example, the size of allocation blocks. Second is allocation file, which keeps track of which allocation blocks are free and which are in use. Third, catalog file, which is a balanced tree or B tree that contains record for all the files and directories stored in the volume. Fourth, extents overflow file, which is a B tree that records the allocation blocks that are allocated to each file as extents. Fifth, attributes file, special B tree file which contains additional data per file or folder. In the future, it will be used to store information about additional forks. Sixth, startup file, facilitates booting of non-Mac OS computers from HFS Plus volumes. And finally, seventh one is unused space. Here we have general structure of an HFS Plus volume. On the top we have reserved 1024 bytes for volume header. Then we have allocation table, extents overflow file, catalog file, attributes file, startup file, and finally the alternate volume header, which has 512 bytes reserved for it, and the gray area in between is the file data or free space.
Flash file system. A flash file system is a file system designed for storing files on flash memory devices. Now, why these files cannot be used for flash drives? There are several reasons, like erasing blocks, random access, wear leveling. Erasing blocks. Flash memory blocks have to be explicitly erased before they can be written to. The time taken can be significant. Thus, it is beneficial to erase unused blocks while the device is idle. Hence, when the flash store is to be updated, the file system will write a new copy of the changed data over to a fresh block, remap the file pointers, then erase the old block later when it has time. Random access. It is the ability to access an element at an arbitrary position in a sequence in equal time, independent of sequence size. The position is arbitrary in the sense that it is unpredictable, thus the use of the term random in random access. The opposite is the sequential access, where a remote element takes longer time to access. A modern example is cassette, where you have to fast forward through earlier songs to get to a later one, whereas in a CD you just skip to the track you want. Wear leveling. Flash devices are consumable parts. One can perform only a finite number of erase cycles on each block before the block becomes bad. To maximize the life of the flash, wear leveling algorithms are provided. Wear leveling comes in two types: dynamic wear leveling, static wear leveling. Dynamic wear leveling addresses the problem of a limited number of erase cycles for a given block. Rather than randomly using blocks as they are available, dynamic wear leveling algorithms attempt to evenly distribute the use of blocks so that each gets uniform use. Static wear leveling. In addition to a maximum number of erase cycles, certain flash devices suffer from maximum number of read cycles between erase cycles. This means that if data sits for too long in a block and is read too many times, the data can dissipate and result in data loss. Hence, static wear leveling algorithms address this by periodically moving stale data to new blocks. In practice, flash file systems are only used for embedded flash memories that do not have a controller. Removable flash memory cards and USB flash drives have built-in controllers to manage wear leveling, bad block recovery, power loss recovery, garbage collection, and error correction.